Welcome, everybody. Welcome to today's webinar. First of all, sorry for a little bit of the IT issues that we got here. Fortunately, there was a link sent that was not was from our preparation and not for today. But I guess now you all have received the correct link to join, and we welcome everybody to today's webinar. In today's webinar, we'll be talking is basically to introduce a powerful new addition to our portfolio. So that is an advanced near infrared light technology analyzer. So it's a crucial advancement that will help us provide even more accurate and reliable solutions to our clients, closing some of the gaps that the pulp and paper industry have and helping us tailor our solutions to address the industry most pressing challenges. So my name is Enrique Milanez. Most of you, or some of you at least, know me. I'm responsible for pulp solutions in the EMEA region. And joining me today, we have Tan Trung, General Manager of Fitnir Analyzer as well. So before we dive in, a quick reminder. So if you have any questions during the presentations, please type them in. So we'll be collecting them and addressing at the end of the session to ensure we cover everything thoroughly. So while you're speaking, please type them in. We'll be collecting them. And at the end, we will address the thing. So before we explore what our technology, which is exciting, and we want to show all the details about it, uh, let's start by taking a look at the motivations behind presenting this analyzer to the market, and how this is a powerful tool for us at the BTG, and it's gonna show an outlook for what the industry could look like in the future. So as you all know, wood-based materials have always posed challenges in processing due to their natural variability and unique composition. So how many times I remember starting up a digester or operating a digester, and we are having very stable wood supply and genetically changed, which is to reduce the natural availability of the wood, and still something would happen on the operation and we wouldn't be able to explain. So even in the pulp industry, despite this significant advancement in biogenetics, we currently facing immense pressure on stable supply composition. So, and recently, due to the climate change, factors like scarcity of wood and stability of current crops. So, what we are seeing right now, which is heartbreaking that it's happening right now while we speak. So, it's very actual in Portugal, the tremendous, devastating wildfires right now in Portugal and also in Brazil, like having tremendous impact on the wood there, and but not only there, droughts and floods that we are seeing as well as we speak in Central Europe. So this is increasing the natural availability of wood and creating even more pressure on this on the wood supply. Also, to add another layer, recently we had a war coming, which destabilized the whole supply, wood supply, creating another layer of complexity on processing these raw materials. Uh, so before we had a gap to understand what is entering the digester, which was known as a gap in technology for pulp processing, and how we can close the loops to optimize it has always been a challenge and a gap. Today, even more important to have a solution, to have something that one can help us see what's coming in the process plant, and two, that we can actually act on it, that can actually close the loop, that can actually use it to optimize the process. So those two things are tremendously important. The second point is on human resources. So it's another quite alarming one. So on human resources, the scarcity of human resources has been a growing concern for several years. And we are seeing increased concentration of people in major centers. So we all know this for 10 or 20 years now, the migration of people to major centers, while the global fertility rate is dropping at an alarming pace. So this scarcity is driving up costs. Obviously, it's harder to get people in our pulp facility, in your pulp facilities, and this is squeezing the margins. So making it essential for us to explore ways to make our process more independent of human intervention. So I remember on this matter, on the and then as if you could move a slide back. So one one thing about this human resource matter is, once a client said to me, uh, which was quite stuck in my mind, said, Enrique, the pressure for digital adoption nowadays has changed. So now for us is not how much productivity we can increase, but if we'll be able to run the machine in a few years without the resources. So human resources scarcity and digital adoption have merged recently, and the pressure for reliable and low maintenance instrument is now tremendous. And to my last point, it's basically the high maintenance costs and the gaps in measurement technology limiting the digital adoption. So moving towards a more autonomous process naturally leads us to the next point. This is reliable and low maintenance instrumentation. So a client that it's also a good friend of mine once said to me, Enrique, we can have the best technology in the market to measure a property that we really want to know. But if you cannot close the loop, or meaning if we cannot use it to optimize the process, it will be just a fancy signal floating on the mill. So basically, if you need to go in the field every now and then and touch it and recalibrate it, it's probably a no use. So I partially agree with that statement. And to navigate these complexities of working, as I mentioned, with the natural fibers in this pressure that we have nowadays of supplies and natural disasters, and to improve margins through automation, which is my second point on the human resource scarcity, the industry needs robust solutions that reduce downtime and require minimum human oversight. So with that in mind, with this outlook that we see, unpredictable wood supply, pressures on margins and resources driving the need of automations operations, and the high maintenance costs that we see on some of this technology, especially on the gaps that we see in the industry, we want to explore what BTG can offer as a potential future outlook for the industry, and how our newly incorporated analyzer can help address these challenges. So I'd like now to give stage to my colleague, friend, and professor who taught me on the topic conference, Tan Trung, who will now guide us through these possibilities in more details. So just a quick reminder, again, if you have questions during the presentation, type them in. We'll collect and address them at the end of the webinar. Tan, the stage is yours.
Well, thank you very much, Enrique. Appreciate the introductions. Welcome to our seminar, and apologies again for the delay in getting this to you with the technical difficulties. So as Enrique talked about this, I'm going to provide you with some information with regards to how we can integrate our analyzer measurements with our control systems so that we basically drive value to the mill. So if you actually look at this back a little bit further and what Enrique is talking about, essentially when you look at the variable costs associated with the mill, you have your fixed costs, but what we want to do is help you find ways to drive down the variable costs. And depending on where you are, there are a few things that actually comes up to be quite prominent. Fiber supply is typically one of the biggest costs associated with the mill. So depending on where you are, again, whether you're hardwood or softwood, but if you look in general, the actual aspect associated with the fiber cost is typically 30, 40, even 50% of the cost of producing a ton of pulp. That's actually very key. So how do we actually find ways to help you reduce that in terms of variable costs? Next component associated with this is the chemical. We all need our chemicals to actually go through our pulping process, and again, depending on how you run, it actually has quite a bit of costs associated with it. Again, what we can do is how do we actually help you improve on that? Energy is a big component worldwide, obviously. Our consumption associated with energy for driving to our pulp operations, all heatings and dryings and so forth. And of course, more ideally now with our excess amount of production of energy in terms of steam, we can use this and alternatively to produce electrical power to actually sell back to the grid. So reducing the costs associated with energy, particularly having surplus of it, is very, very important. Couple other components associated with the variable costs, obviously labor, depending on, again, where you are, but how well we run the mill, how well the mill is maintained, affects both in terms of materials and maintenance costs. So again, that's another component associated with what Enrique was talking about, the scarcity associated with personnel availability is also very, very key. So from our perspective, we want to help you in terms of increase the efficiency and reduce the variable costs. Some of these actually allows us to be more competitive worldwide. Okay, and the need for information for this is that we'd have to have some of the fundamental properties associated with the actual chemistry, the process information that allows us to improve integration. But not only that, we have to go forward and go one further step than that. It actually is to integrate these measurements with automated control systems towards more digitalizations and advanced control process. And that's where we can actually see the benefits, is to be able to measure what's actually in your process, use this information to actually drive down variability, and then of course make the target shift change to allow you to actually make the necessary improvement and provide the necessary gains in your process. So if we look back now a little bit and actually look at the actual pulping process wise, we see this essentially as two cycle process. I kind of label that here as a craft pulping process wise in two cycles. On the right hand side is our sodium cycle, and our left hand side is our calcium cycle. And depending on where you start, it doesn't matter where you start. So it's actually a cycle in a perspective that one area impacts another area. So and whenever we can help to improve the operation associated with this one area, the next stage is your new customer, that's your customer, and you can actually help out in terms of reducing and improving the overall operations. So we look at the dissolving tank, for example, if we start there, how do we actually produce the best green liquor possible, stable green liquor possible? How well we will actually run that process has an impact on the overall slaking and causticizing area. And of course, that produces the necessary white liquor that allows us to feed into the digester. And of course, the chip quality affecting how we actually operate the digester. And of course, again, as I mentioned, how well you do that has a huge impact on the washing, the bleaching associated with this, and so forth and so forth, to the recovery of the weak black liquors through the evaporators to concentrate our black liquor to heavy black and strong black that basically goes back to the recovery boiler. So that has a huge impact. Okay, so that's where our liquor cycle starts and actually revolves around. One area that's actually very important for us is obviously is the slaker and the causticizing area, because here it's a merger between that of the sodium cycle and the calcium cycle. So how well we run the causticizing area actually dictates the actual consumption of the lime that actually goes into the slaking process. And of course, this affects the kiln. And the kiln, still being the #1 consumer of fossil fuel, will have an impact associated with our energy and energy consumption and so forth. So we actually look at this as a cycle. Again, as I said, if you can improve on this in any way we can, it helps us throughout the liquor craft recovery process. So if we look at this, and we may ask, what is that chemistry? Well, if we look at the reason why I started with the dissolving tank and the recovery boiler is that this is where we actually generate a lot of our chemistry. So if we actually spray liquor into the recovery boiler, we combust this, undergoing the oxidation process. We basically oxidizing all of this chemical to sulfate and carbonate. Okay, as the smell drops down into the bed itself, it actually lacks the oxygen, therefore it actually undergo a reduction process. In the presence of the carbon that's there, it actually will form and convert that sodium sulfate over to sodium sulfide. So we actually look at now the smell compositions itself. The smell comprises approximately of 2/3 of this as sodium carbonate, approximately 1/3 of this as sodium sulfide. And depending on how well you reduce the chemicals, you may have some left over associated with the sulfate itself, therefore the term reduction efficiency. So our chemistry starts here. We produce a lot of this in terms of the carbonate, the sulfide, and some dead load component. This is what we call as the dead load, as the sulfate, because it doesn't help us with the actual pulping itself. We now move forward and we look at that carbonate. We have that carbonate in the green liquor. It goes into the causticizing area. In the slaker, we add the lime itself, and that lime helps us to convert that carbonate over to the sodium hydroxide. Therefore, what's important for us is how well we convert this is our causticizing efficiency. Okay, so that's our second component associated with the dead load. How well do we convert this over to the hydroxide will have some residual carbonate left over. So again, that's very important for us to actually consider and control, and therefore needing the actual measurement associated with the actual chemistry of the liquor. Okay, so but conventionally, when we look at the overall pulping of the operations here, we rely on what we call as inferential measurements. Inferential measurements meaning in measurements that actually infers at some of the chemistry that I just talked about. So for example, at the dissolving tank, we tend to use density as a way to infer the total chemicals that are present in there. And this density could be installed at the dissolving tank to look at that, or at the clarified green liquor going into the digester. But that doesn't tell us the exact chemicals that's actually in there. It just infers whatever is dissolved in that liquor. Okay, so there's more problems associated with this, but I'll show that a little bit later on. Through the consticizing area, we actually use other techniques such as conductivity. And here we actually use conductivity to infer again at the actual amount of the sodium hydroxide that's being developed throughout the consticizing process. Into the digester, same thing, conductivity is used, temperature is used. But again, we use this as a way to actually infer at what the true chemicals are. To get a bit more information associated with these liquors and the chemistry associated with it, we actually run manual tests. We run our standard ABC tests, but we know that these manual tests are not frequent enough to allow us to actually get at the automated control to operate better because of the slow response associated with this. Okay, so why not just use density, as I mentioned? Why not just use that as to give us the information necessary for us to control the process? Well, here I have the plot that shows density and the actual TTA, or the total titratable alkali of that liquor, in blue and in green. Okay, so as you can see here, density tracks with TTA quite well until such time as it starts to scale over and it starts to drift away. As you can see here, the actual response associated with the density still lines up well with the response of the actual changes in TTA, but now it's drift off. So somebody has to go out there and clean that density probe. Once you clean that density probe, you can see that it tracks over again, but at some point it starts to lose that measurement. And if your measurement, as shown here on this side here, it starts to scale over and becomes unresponsive, that density starts to drop. And if the density control is on, it'll try to actually cut the weak wash going in to try to bring that density back up. But if that's not real, then now you have a high TTA that is actually rising. In this case here, you could rise to a point that you go into a saturation zone, therefore seeing a lot of depositions in your process line. So again, somebody has to go out there and clean that to actually bring that back together. So density is a reasonable measurement for the short term, but is actually not the best for the long term. And it actually may actually induce some of the variability associated with your liquor cycle. So that's basically why I said be careful, because you have to have the right monitoring tools and to maintain the density measurement to ensure that it doesn't cause more problems in your liquor cycle. In the slicking area, some of the biggest problems associated with this is how do we actually add the lime that's actually required to actually convert that sodium carbonate over to sodium hydroxide. So I've got a plot here, a basic graph here that shows essentially the concentrations in green liquor of the sulfide, of the carbonate, and then a little bit of the sodium hydroxide coming from the weak wash. This is referred to as the TTA, or the total titratable alkali. So what we would do in the slaking process is that we basically would dose the lime. That dose to lime will convert some of that sodium hydroxide, carbonate over to sodium hydroxide. But since we can't actually convert everything over, because this is a equilibrium reaction, you're going to have some left over in terms of the sodium carbonate. Okay, if we try to dose too much of the lime coming in, then we're going to have what we call an excessive lime that's actually going in there. Excessive lime in the liquor process is bad for this case here. Carryovers, unsettling associated with the clarity issues associated with white liquor clarity. So that has a huge impact of the white liquor going forward in the digester. Now, as shown here, the amount that you actually achieve in terms of the cost of sizing efficiency will always be lower than the actual equilibrium that you can actually achieve. So controlling this process is very, very important. Okay, so that's why we actually want the chemistry associated with this, so we can charge accordingly. So as I mentioned earlier, manual titrations and automated titration systems give you more information than density and conductivity. But in the case here, these acid-based titrations or back titrations associated with this with acid allows us to calculate what the actual base we have in the sample. This is referred to as our ABC test. The manual ABC test works, but it actually is a bit infrequent, slow, typically 15-20 minutes in terms of titration time, and there's some other issues that kind of creeps up and potentially cause some influence on the actual measurements, such as pH calibrations, the chemical strength, chemical makeup of the acids associated with this, and whether you have temperature impact associated with pipetting in terms of the sample has an influence on the volume, solids content, and of course, all of these can be automated as well, and they do tend to work and provide information, but it does take more maintenance to maintain these systems. And additionally, there's costs associated with the chemicals and the technician's time to actually maintain these systems. So in our case, our customers and so forth has asked us to develop new ways to actually measure these liquor chemistry. And that's basically what I want to talk to you more about today, and the concept of using FTNR. But before we go on, the whole concept associated with process control and optimization is this. We have to be able to measure what's actually in our liquor cycle. So if I show here, if the gray line here is your TTA of that concentration with large variability, then you're going to have a large distribution in your data set. What we want to do is reduce that variability, reduce the distribution of that data. And if we can reduce that distribution of the data, then we can talk about moving that target in terms of the actual operation itself to some more optimal condition so that we can actually improve on the overall process. But with that, we need the fundamental properties measurement that I just referred to. And that leads us to the concept associated with using the near-infrared system. And some of you may ask, what is this near-infrared analyzer? What is a near-infrared system that we're talking about? Well, essentially, we're talking about using light in terms of the measurement. Go away from that, the use of the actual acid-base wet chemical analysis, and utilize light. But in this case, for us, the light is a little bit different. What we're looking at is the infrared light associated with this, with the spectrum. I've shown here all the actual spectral range associated with this. On the left-hand side is our high energy source, gamma radiations, and so on. Goes down to X-rays, ultraviolet. And as we move to the right, we go into our visible region, our RGB, red, green, blue. And just beyond the red is our infrared, and further to the right, it's microwave, and even further to the right is our radio wave. High energy source on the left-hand side, lower energy source on the right-hand side. Now, as I mentioned, just beyond the visible, the reds and the visible region is our infrared. Our infrared region can actually subdivide that into further 3 regions, what we call as the far infrared, mid-infrared, and the near-infrared. In the mid-infrared region, we are very familiar with this in the university days, where we use this to actually measure fundamental bands such as aldehydes, ketone, and so forth. Far infrared has many applications. I've played with these in the past. Very good in terms of medical imaging systems, as well as security applications, because we can actually see through some of the clothings and so forth to look at concealed weapons and so forth, or look at temperatures of objects to give information associated with the days of fevers of SARS back in when I was working on these. Where we were looking at is the near-infrared region, and it spans from approximately about 700 to 2500, but more importantly from about 900 to about 2500 is our nanometer range. In this region here, we can actually have a few things that are actually quite handy with the associate with the near-infrared region, because the longer wavelengths associated with these light, we can actually pass through particulates in the sample. I have an example of a pictures at the bottom there with the left-hand side of image using a visible camera. of that rig out in the ocean, and in the case here, a near-infrared camera of the same image of the rig out in the ocean. As you can see that even in a smoggy day, the actual near-infrared light can actually penetrate through the actual particulates in the air and allows us to actually see that rig out in the ocean quite visibly clear. And what's important for us in this case here is that when we look at our samples, there are many solids in the sample, so the ability to actually see through some of these particulates is going to be very, very important for us to be able to provide the necessary measurements. Now, how it works is this. We have a light source, and the light source is a safe tungsten halogen lamp source that we actually have inside our spectrometer. We send this light down fiber optic cables, and this light is now coupled to our process flow cell that sits out in the process area and where we have our sample. When our sample sees this infrared light source coming in, it will absorb some of that energy. And some of these absorbed energies, and what it causes it to do is actually undergo what we call a molecular vibration. So in other words, the energy is absorbed, the molecules absorb the energy from the light and actually vibrates. Okay, so they actually moves faster in a sense here. Now, our light source is low. It's not strong like X-rays and gamma radiations and so on. So it actually would just cause the molecular vibration, therefore the term molecular spectroscopy. What's unique about this is that the molecules absorb different frequencies of light, actually gives them the vibration that need due to the fact that they have different molecular makeup, the electronic interactions associated with and the bonds associated with these molecules actually absorbs different energy to vibrate. Therefore, we can actually record these different frequencies absorptions with our infrared detector, and then we can convert these frequency domains using Fourier transformation, therefore the FT systems, into our characteristic NIR spectra that allows us to actually do a couple things: determine what's there by the frequencies that they absorb, and how much is there by the height and also the band and so on that actually shows up for these molecules. So you may or may not know it, but there's actually a very, very big near-infrared camera and detector that's out in the space. It's called the James Webb Telescope, and this James Webb Telescope actually has a few detectors in there, 3 of them specifically, a mid-infrared camera and also 3 near-infrared cameras. And these near-infrared cameras and detectors are now very, very sensitive, associated with to actually be able to pick up the light from the various dark regions of our universe to give us information is actually very relevant to what we're trying to do in terms of space exploration. So in the case here is that it actually near-infrared spectrometer, case here in the imaging system, and also a different camera system with a mid-infrared camera. What's also unique about these James Webb is that it actually very, very large primary mirrors that actually collects a lot of light associated with this to focus onto these detectors that we have. Now, what can we do with these things is actually very neat. The systems itself, because you can actually see the actual molecular makeup associated with this, you can actually now pick up from planets, exoplanets and so forth, things like methane, sulfurs, even water vapor that allows us to actually see what is the makeup of the actual atmosphere for these exoplanets. Gives new meaning to actually space exploration. So what we do with it is very much the same thing. We actually measure these actual molecular vibrations associated with this to give us information necessary to actually determine what's actually present. For us, in the measurement capability of these systems, we zero the system all the time. We zero the system with water. So every hour, we actually zero the system to prevent any sort of drift that occurs. And you can see that the water spectrum is quite boring. It's a broadband black body radiation, if you will. Now, if you actually scan a sample, you can still see the background associated with it, but you're starting to see features associated with this now. If you subtract away the background to give us the absorbance spectrum, this absorbance spectrum shows a few things. One, where these frequencies occur associated with the actual peaks themselves tells us what kind of molecule is actually present. And of course, how much they absorb in terms of the energy and intensity gives us information associated with the actual chemical compositions and the concentrations associated with this. So that actually allows us to do something quite unique. The uniqueness is that we can actually tell us a whole bunch of different molecules all when we scan all these frequencies all at once. So we don't have to actually run separate titrations, if you will, for any particular makeup. We can actually scan the frequency range and pick up various molecules, various absorptions, tell us what kind of chemicals is there and how much is present by using this particular molecular spectroscopy makeup. So the example would be is that for here we have scans associated with white liquor in our spectra. We scan here from 11,000 to about 7,000 wave numbers, and you can see that this particular peak around this area here is sodium hydroxide. In particular, it's 10,350 wave numbers or reciprocal centimeters, and this absorption is the same whether it's in Sweden, where I am right now, or in Canada, or in Indonesia, or in India. It will be all the same. As I mentioned earlier, also be in space as well, because the molecular makeup associated with this and the actual Hooke's law dictates that these frequencies of absorption is well defined and can be used to determine that this is sodium hydroxide. And of course, the height associated with this allows us to actually calculate the concentrations. So by scanning all the frequency associated with this, we can actually pick up all of these chemistry that we have in our liquor with the single scan. So how these systems are hooked up as a way to actually do measurements is quite unique. Because the fact that we scan these systems quite fast, these samples quite fast, the scan time for analysis is only 45 seconds. We can actually utilize one single unit, what we call an SRS, or spectrometer rack system, that can be located in MCC rooms centralized in the mill. We can run fiber optic cables to deliver the light out to the actual flow cell that I mentioned earlier, and also the fiber optic cable to come back to the detector. We can have up to 8 detectors, so we can actually span various areas of the mill. In this example here, we have for the digester, looking at multiple samples coming in. So it could be white liquor, upper circulation, lower circulation, extraction, wash liquor from the digester, giving the complete profile of the K-Mir digester. We can also run fiber optic cable to another field sample station, or the FSS. In this case here, an example of a recovery boiler. In this recovery boiler, we have 2 dissolving tanks, so we can take the left and right, and the east and west, or whatever the case, of all the various raw green liquor from the dissolving tank, as well as the weak wash, and measure that. We can run fiber optic cables then to the recos area on the FSS there to look at clarified green liquor, slicker, first causticizer, fourth causticizer, and so forth. And of course, we can also do chlorine dioxide generator as well. So the application is quite unique. We can actually apply one central SRS unit to actually connect to various field sample stations throughout the mill to actually provide an integrated measurement that allows us to actually use for process control. So here's some example of this. The system here shows examples of a left-hand picture here of a system measuring chip properties. In this case here, a dedicated system looking at chip moisture and chip density, basic and bulk density, as illuminated on the conveyor. The central picture shows a digester unit measuring white liquor and weak black liquor from the various stream to give us the complete profile of the actual digester liquor chemistry. Of course, also on the digester, we have the chip, so that allows us to do complete control associated with the operations. Far right-hand side picture just shows an example of a field sample station for the recovery and recon system, as I mentioned earlier. And you can bring various process samples into the actual analyzer here, and allowing us to actually flow through the flow cell for the measurement of these samples. Now, because of the fact that we're looking at molecular absorptions, we can apply this to many different products, many different samples. We focus on the current operations of the mill, but as we expand in the future in terms of more biorefinery and biochemicals, we can actually apply the same principle to the actual measurement itself. So just a bit closer up view associated with this particular mill. We have multiple samples coming in from the various process. These liquor samples flow through into the cell where we capture the sample. We actually measure the flow and temperature associated with it to give us the information, and that light that actually brings back to the detector allows us to scan the sample and actually quantify the actual chemical compositions. In this case here, the example is a picture of the green liquor and the white liquor measurements throughout the recos area for a mill. So just quick summary associated with the technique itself. We have the SRS, which is the spectrometer rack system that has the spectrometer. We send light fiber optically over to a field sample station that is situated out in the process area, allowing us to run lines into the actual FSS to bring liquor to the cell. And that's light that goes through the cell containing the information associated with the molecular vibration, gets back to the spectrometer where we record the spectrum, calculate the concentration, and send that off to the DCS. Okay, so each of these SRS system can actually have up to 8 field sample stations because we can actually have 8 detectors in there. Each detector services one cell. Each of these field sample stations, we typically provide 6 sample stream coming in. So all in all, we can actually measure up to about 48 samples across the various areas of the mill. As I mentioned earlier, the system self-flushes the sample lines. After each analysis, it flushes each of the lines back to the source to clear the lines. It also flushes the cell with demineralized water, and it zeroes the system every hour to allow us to actually maintain the operations of the actual analyzer without the issues associated with drifting. If you open up that box a little bit more, just give you a little bit more information. Liquor comes in, comes out the top, and actually returns back into the process. Fiber optically brings light to the cell, through the cell, and then back on another fiber optic cable that goes back to the actual detector. So again, here in this case here, if you look at the sample interface, there's actually no valves, no pumps, just basically no acids, no chemicals, just basically liquor coming in, capturing it, and then scanning, then flushing the samples. The measurement capability is quite strong for the digester, as I mentioned, measurements of the white liquor giving you the complete EA, AA, TTA, the sulfidity, and also the carbonate and CE values. In addition to that, the weak black liquor down the digester, we measure the true residual effective alkali, meaning the actual sodium hydroxide present in there, the total solids, the lignin content, and the organic and inorganic content associated with this. In the recovery area, we cover all areas associated with this. We basically have raw green liquor, clarified green liquor for complete measurement, including the sulfate, giving us the actual reduction efficiency. Through the slaker and the consensizers and into the final white liquor, again, same aspect, complete ABCs associated with this. But we have expanded to other areas of measurement. For example, in the weak black liquor measurement, giving us the information necessary associated with the residual effective alkali, the organic, inorganic content. And if we've expanded further, so for some mills that are actually interested in the chloride, we can measure the chloride content associated with in the liquor because it has an influence associated with the actual scaling propensities in a recovery boiler. Chlorine dioxide generator applications measuring the direct sulfuric acid concentration, the chlorate, and the solids content. As I mentioned, also in the MC system, this is our chip analyzer system measuring the moisture as well as now the basic density, bulk density, extractives, and so forth. So minimum measurements across the mills, and I just wanted to show some of the applications associated with that as we go along. So how do we use this information is quite key. So Enrique talked about this quite a bit. The aspect associated with measuring it is okay, but how do we actually take advantage of that to give you improvement in the overall process? That's actually something very important. So we all know this, and from the perspective of the fact that from a digester operation, white liquor chemistry is very key. Okay, so basically we have the aspect associated with the EA from the actual white liquor. As a matter of fact, many papers have demonstrated that the white liquor EA is the most has the most contribution to the actual kappa variability. But wood species, another one, chip size distribution, chip quality in terms of moisture would be very key. All of these aspects affect the actual variability of the kappa and yield. So we want to be able to actually provide you with information that we just talked about and how to utilize this in terms of control. So just to expand that a little bit further from a digester application perspective, because of the fact that we can actually measure the white liquor coming in, the actual various black liquor from the different zones of the extractions, we can actually give you the complete profile associated with the actual digester through one of these FSS associated with the hookup to the SRS itself. Now the information going to the DCS can now be used and actually used for process control. So the integration in this case here would be is that we have the actual chip moisture content coming in that has an impact in terms of the feed forward, in terms of the production, the white liquor information from the alkali charge associated with this, the various extraction residual alkali all the way through the digester, and then feeding this back to actually control the overall cooking profile down the digester. And of course, as it comes off from the blow line, measurements associated with things like the actual SPKs for kappa would also provide necessary feedback. All of these would then be used to actually part of the max control, max cook, to actually provide you with improvement in the overall operation of the digester. So this information has never been readily available, as I mentioned in the past, whether it's usually a conductivity-based measurement or a titration base. But now we can actually utilize the analyzer to give you the necessary information for the actual control of the system. So white liquor allows us to do EH white liquor charge, compensate for changes in the actual white liquor variability from the white liquor production and the recall side, sets the white liquor flow, and of course ensures good sulfidity for monitoring the sulfidity. Black liquor now looks at the residual alkali coming back, compensate for changes in the chip moisture and chip density due to the consumption of the alkali, and that allows us to actually manipulate that whole overall process. And of course, the SPK allows us to provide us with the kappa as it comes out from the digester. So some of these have already implemented. The fact here is that we actually have measurements on this particular digester, before and after the control. So this is the residual alkali on one of their extraction zones. And now you can see that the onset of the control system will manipulate the overall process to allow us to actually stabilize that residual effective alkali. And what does that transfer over to? That transfer over to is just stabilizing the actual kappa out of your digester. So that's actually very key and has been demonstrated can be used for that. But the advantage here as we move forward is that we can measure much more than that. We can actually measure the lignin content, the total solids, the organic, inorganic content. So all of this information allows us even more information that cannot be seen before. And all towards the use of this information for semi-autonomous and autonomous control as we move towards Industry 4.0. So that's a bit about the actual liquid chemistry in the digester. But one of the other aspects I mentioned earlier is the chip application. Chip moisture is one of the key things that affects the digester production. So the ability to actually measure this typically now is that we actually take samples from the process. We actually would then take that to the lab and then segregate this and then dry them in the oven, hopefully multiple times to give us a bit average associated with the moisture content. But to do this, we dry it in the oven at 105, 106 degrees overnight. So the actual moisture content is not very frequent information that gets fed back. So we assume some sort of moisture for the digester production. Well, in this case here, we have now, they basically have an online system that measures the actual moisture content of the conveyor feeding into the chip bin, and that allows us to provide information every 60 seconds associated with the moisture content of this chip into the digester. Illumination here on the chip bell itself, we capture the actual light coming back and we send that back through fiber optic cable, and that allows us to actually record the spectrum. So this is some data from mill that's been running for quite some time. In this case here, over approximately 4 years, 3-4 years in this, and this is laboratory in blue and the actual analyzer measurements. You can see clearly that over the years they've analyzer validated very well associated with this. Our typical accuracy associated this is within about 1 to 1.5% associated with oven dry methodology. So information from that is good for digester control for productions, but what else can we measure? We can measure also things like the bulk density and the basic densities I mentioned associated with this. So on that same analyzer system, we can actually apply the measurements to provide the additional properties that we don't actually need additional equipment to do, utilizing the same spectroscopy-based information from the captured spectrum. We can actually provide more information. So that's an advantage of using spectroscopy techniques. But from an example of how to use this, we basically have applied this where we measure the moisture content, and then we utilize the Mills weightometer system. If we have the wet weight associated with this and we have the moisture content, then we can actually calculate the actual mass of wood chips. And if we know this mass of wood chips and take into account some of the actual densities and so forth that we can measure, now we can actually have an estimator, a controller system that would actually manipulate the actual chip meter speeds to actually charge a digester properly. So this is an example, and it's a paper that's already been published that actually shows you off control on the chip meter speed to an automatic system utilizing this type of setup. It would manipulate the actual chip meter speed such that we actually now stabilize the feed rate to the digester, giving us much better production, as you can see here in the orange color, as compared to the blue previously, where you're now basically undercharging the digester and losing out on some of the production itself. Now, in this case here, undercharging the digester is one thing, but you could also overcharge the digester. In both cases, actually bad for the digester operation and has an influence on the overall kappa variability. So that's been shown. The mill itself has reported significant savings associated with this in terms of production rate control. So the reduction in kappa variability was very key, 50% reduction in kappa variability, changes in white liquor consumption because of the fact that now we can actually charge the digester properly with the EH white liquor ratio. They saw a significant increase in production itself and attributed about $4 million towards this. So again, that's actually captured and presented by the actual mill that did the paper with us. So some of the other applications as we close off in this seminar, recost recovery applications is very important. As I mentioned, if we go back in the liquor cycle now, we basically have the means to actually measure the liquor chemistry, allowing us to actually control the process better. So when we actually try to control the recovery and recost liquor, we always go back to the concept of using Goodwin's curve. Okay, so what the Goodwin's curve show here is this. We have a TTA and we have the equilibrium processing efficiency. We have a couple lines here. The blue line is that equilibrium that I talked about earlier, but since we can't run into an equilibrium associated with this, we have to run somewhere further down, and some mills would choose about 95% of that equilibrium line. Okay, so if your operation is here, you can now look at the ways to actually improve this by both increasing TTA as well as increasing consensizing efficiency. So if you're running at 120 grams per liter as Na2O, then you can actually look at opportunities to move this up further, maybe to possibly 125, 128 grams per liter as Na2O, and improve on the overall consensizing efficiency. Moving up in this and to increase the TTA, reduce the amount of water. Moving up in this here reduces the amount of carbonate dead load, and we have higher in terms of both the actual white liquor strength in terms of the CE as well as lower dead load. So maximizing this is actually very important, but in order to actually do this properly, you have to stabilize the liquor and the TTA itself to ensure that you can actually target the actual CE properly. So that goes back to the point that we have to be able to measure the liquor chemistry And how we would do this is this. We have essentially now a standard dissolving tank with a density controller. So basically smelt comes into the dissolving tank. We have a weak wash addition to this based on the density itself. But as I mentioned earlier, the issues associated with density alone has potential impact on the overall stability of this liquor. So what we want to do with this is we want to actually now measure this with the Fitnir system and actually utilizing max associated with this, both density and the TTA. And as the density starts to drift, the actual measurement from the analyzer would correct the density, which can now be used to a proper TTA set point, which cascades down to the density controller, affecting the actual flow controller to affect the actual weak wash going in to dissolving tank. So we do it this way as a nested aspect associated with this. The fact is that everybody is very used to density control itself. This outer loop allows you to actually tune that, but to run that to a specific TTA set point. So the improvement is quite significant. Here's an example of the mill where we basically have a TTA prior to the actual analyzer being installed. About the control being installed. The analyzer shows quite a bit of variability associated with these measurements. We start the actual control associated with this, and you can see now we reduce the variability significantly. And from that point, we make a change associated with this set point, and you can see that it comes up in concentration and continues. But in this case, what it shows is that we've now reduced the variability significantly. That 80% reduction is shown here with stable TTA. Now we can make an improvement to the actual recost by making a shift to the actual TTA itself, improving the feed forward of the liquor to the recost area. One other aspect associated with this is the trim control. So that's the raw green liquor. The clarified green liquor that goes to the slaker itself can be done the exact same way. So here's your clarified green liquor going to the slaker. If you have this stream, that basically allows you to do closed loop control associated with weak wash addition. If you have density, that's great. And we can use the same way to actually utilize information with the actual analyzer measurement for the TTA or the carbonate. Use max sweet to actually do the actual control associated with this with a TTA set point cascading down to the actual full controller to manipulate that TTA that goes into the slaker. Now, this is very important. As I mentioned, if you don't actually take anything away from this presentation at all, this will be important to be able to control and stabilize that green liquor going into the slaker, because that allows you, as indicated by the Goodwin's curve, to be able to actually target the actual CE properly. Okay, so implement this would be very, very key in stabilizing the actual green liquor going into the slaker. But better yet, implement downstream in terms of the upstream instead of the dissolving tank, stabilize that as much as possible before getting into here. So here's an example of that. We manipulate the weak wash trim flow into the green liquor, and that allows us to basically stabilize the clarified green liquor going into the slaker. So the standard deviation on here is 4.3, whereas here is about 0.7. Again, stabilizing this 50, 60, 70%, allowing you to actually target the CE properly. But to do that, you have to have the measurement for feedback, and that system would then manipulate the weak wash trim flow as much as possible to stabilize that clarified green liquor TTA going into the slaker. So last part to this associated with this is really all about the actual slaker control. That aspect really is now we have the measurement of the analyzer for the TTA and the carbonate, allowing us to actually calculate the right amount of actual lime to be added into the slaker. That's the feed forward function associated with utilizing the information from the analyzer. And then we measure it afterwards, either at the slaker or the #1 consisticizer, which is the preferred spot. Utilizing this information in conjunction with the max suite to be able to actually control the actual lime addition, the lime screw itself that adds the lime to the slaker for the reaction. Okay, so that's measurement both from a feed forward control as well as a feedback. And then measurement at the last consisticizer allows us to actually manipulate things a little bit more in terms of a final adjustment to ensure that the white liquor going forward has the best liquor CE, highest EA possible, most stable EA possible to the digester. So that's kind of what you would do in terms of a closed loop control through the slaker and costicizer area. And the concept really is again, improving of the overall process. Here's an example of the final costicizer on the CE. This is the line manipulation to the slaker and the actual fourth costicizer CE coming out. Off control, on control, and off control. As you can see here, the variations, and then on control stabilizing that CE, and off control again, clearly showing that at the set point, the lab test and the Fitnir all match up quite nicely. So the benefits is quite strong. We have demonstrated this with many different applications throughout the world. Recost area, reductions in energies and chemical, very significant, stabilizing the actual liquor chemistry. Digester improvement in terms of the control, in terms of reducing kappa variability and improving yield, quite significant there. Chlorine dioxide generator, I haven't shown that here in terms of an application, but same principle applies to the chlorine dioxide generator. We have applications on chips, obviously, as I mentioned earlier. The system there on production rate control provides significant amount of benefits associated with this. And then lots of other applications that we can describe and we can help you with. Including lime mud solids, for example, is another application that would be very, very key to minimizing some of the energy consumption in the kiln. So applications far-reaching, our integration associated with BTG and the max control suite-wise is quite significant. Now we have the capabilities, as mentioned, for chip measurements through the digester, white liquor, weak black liquor for the whole fiber line side associated with this here. Our measurements on the solids into soap applications we have now developed associated with that. Lime mud properties through the slaker in terms of the green liquor from the dissolving tank through to the clarified green liquor through the slakers and costicizers, and of course applications in chlorine dioxide generator associated with this. And last but not least, the application that's used, the same system that was used for the chip analyzer can also be used for power boilers, such as the measurement of the biomass associated with these. So well-integrated system, but as I mentioned, Enrique mentioned earlier, measurements and control goes hand in hand, so we have to be able to actually provide both the measurement and the control aspect to provide you with the benefits for the mill. So the concept for us is key. The integration associated with this is the measurement itself with BTG and with Fitnir, allowing us to actually incorporate this data into the data parks suite, control suite, and of course utilizing this information, using this information for visualization, analysis, and of course moving forward and utilizing this information to optimize and run the mill to provide you with advanced process control. All ties into what we talked about in terms of addressing some of the needs for the industry right now. So with that, thank you very much for your attention. I just showed some example here associated with some of the mills that have worked with us all throughout the world and the applications that has been achieved and the benefit that's been achieved. Thank you very much, and appreciate your time today, Enrique, for your introduction. Yeah. And if there are any time for questions, and I do apologize again for the delay in getting the presentation started, and hopefully you have some time to discuss further.
We got some questions coming in then, so let me start with the first question that I got here. So it's related to plugging. So there's two actually questions related to impulse lines and plugging. So I'm combining both of them. So the question is, we've had difficulties with sampling white and green liquor in the past due to frequent plugging. Have you experienced similar issue, and how can plugging be minimized? The other question that it's related to this is, as the sample lines are impulse lines, is it the material stainless steel? I guess, is there any chance of jamming as we are dealing with the high temperatures? So if you can comment a bit about that.
Yes, certainly. Yes, the concern with regards to line plugging is always the toughest in terms of the any analyzers actually, and how we actually deal with that. We actually have to come up with a way to handle this. Um, we back flush the lines with demineralized water. So we actually employ a high pressure, in the case here, high pressure 150 psi to 200 and something psi, depending on the application, where we would actually back flush the sample lines all the way to the tie-in point after each analysis, therefore allowing us to actually minimize any plugging associated with this. The other aspect we have to remember is that we utilize smaller tubes. Now, to answer the second portion of it, we use stainless steel 316 stainless steel tubes. And the advantage of the tubes is that it provides us with high velocity. So we bring sample to the analyzer quick, but also the small tube allows us to what we call back flush in a plug flow format, allowing us to get rid of all the liquors in there very quickly. And that's how we actually have implemented and actually avoid line plugging. The other aspect also to remember is that we ask for clean water. We typically like to have demineralized water or very clean condensate water so that we can actually minimize, because the scale formation is from the carbonate and the actual minerals in the water. So if you actually provide just standard mill water, that's actually not something we want to do. So that's basically how we maintain these systems, and these systems were run for years without any issues associated with it.
Thank you, Tan. So, second question here, I think that's a quick one. How much time it would take to analyze one sample? So, how much time? And well, maybe you can comment on the different aspects of it, different samples, and what would happen with the
Yes, of course.
sampling
Yes,
time.
of course. And that's a very good question also. As I mentioned during the presentation, the scan time that it actually takes to actually acquire the spectrum to calculate for the concentrations and so forth is only 45 seconds. But there's also time that's required for you to actually bring the liquor sample from the process tie-in point to the actual flow cell. So that may take 30, 40 seconds, depending how far it is away. So that's why we actually like to place the FSS close to the process so that we can minimize that delivery time. And that's also why we use smaller tubes. So, and then we also back flush, as I mentioned earlier, that might take another 30 seconds. And we also actually do the scan, that's 45 seconds. So a typical analysis time that's good for a sample, it's probably somewhere in the range of, for example, white liquor, 3 to 4 minutes, okay? Because it basically allows us to bring liquor in, back flush the cell afterwards, the scan time. So probably about 3 or 4 minutes. But for samples that are very, very dirty, so for example, we have a raw green liquor that contained, let's say, 2,000 ppm of solids, that might take something like maybe 5 or 6 minutes, because we do actually allow the samples to settle somewhat.
Good. Thank you, Tan. So I'm filtering here. There's another question. I think this question is more related to application, so I combine those two. So is it and I think you showed this, is it possible to use the analyzer to predict or to know soap content in black liquor? Are there any limitation on the solid concentration? And the next is it possible to measure sulfate and sulfite? So a little bit of applications, I guess.
In black liquor, I would assume.
I would assume yes.
Yes. Okay. So the application for the black liquor resins and fatty acids and soap has been developed for one of the mill. So it happens a lot with mills. We install these systems, it runs well, and then the mills would come back to us and say, what else can we measure with this spectroscopy technique? So we basically end up helping the mills to develop this exact application where we're measuring the incoming weak black liquor into the separation tank to look at soaps and the content. So we were able to actually calibrate for resins and fatty acids as well as total soap. And then we measure it before and after the skimming to give us an indication associated with what the efficiency of that would be. As for sulfate and carbonate concentration, that is in development. That is actually a very, very useful information from a recovery boiler operation perspective, because it allows us to, you probably alluded to earlier, the dead low content associated with these would go into the liquor and may cause Burkite formation or dicarbonate formation that scales in the process. And mills are looking at this as a way to mitigate some of these issues. to come, actually. It's actually in development right now. So we're collecting samples with the mill and creating the models associated with this. I think there was one more aspect to that, the limitation on the overall solids content. We have gone up to about 60% of the actual solids with the black liquor going into essentially into the evaporators application now, but we have not gone further into the aspire black liquor, for example, such as 70, 80%. So 60 is the limitation right now is what we work with.
All right then. Next question regarding the chips, the wood chips application. So there's two things. One is, does the snow or ice on chip surface has an impact on the analysis moisture? And second thing is, if we mix different wood chips, how the analyzer handle variability in wood chip composition during the moisture measurement?
Yeah, so that's a very, very good question. I'll answer the first part with regard to the snow and ice. Coming from Canada, yeah, that's not something that we take lightly because we have to deal with this all the time. Some of our winters get up to minus 40, minus 45 degrees. So that's one of the reasons why we actually went with a full spectrum system. It costs a bit more in terms of the actual spectroscopy technique, but we had to be able to actually separate out what we call as free water and frozen water. So the aspect associated with the molecular spectroscopy is that it can actually tell the difference between the state of the water. So when we actually calibrate the system, we calibrated the system to go from minus 30 or minus 25 degrees all the way to 60 degrees, allowing us to actually separate out by looking at the actual bound and free and solid state water content, allowing us to differentiate these things. Okay, so that's very key. We've been very successful at that, and that's one of the key criteria that we develop using our full spectrum system. As to the aspect associated with mixing of the actual wood chips themselves with various species coming in, Canada is exact that, where we have many different mixtures, SBF, spruce, pine, fir, could be mix of hardwood as well. We have aspen, maple, all these aspects associated with this coming in. The spectroscopy technique, again, comes through for us. In this case here, we are looking at the aspect associated with the actual water absorption, allowing us to actually pick out what we call the fundamental properties of the absorption, which is irrelevant associated with the actual wood material, because we're looking at specifically at the water absorption band.
Okay, so now the next question, I think it's related to the different sampling options. Then here it says, so all the sample of liquors will be passing through one sampler, or is it different samplers for each position? Is it max in 8 in a box? So maybe explain it as it's max 8 in a
Yeah,
box.
that's a very good question. That's a very good question. So these field sample stations actually operate all in parallel. So the example that I showed you earlier with the 4 field sample stations, they actually all operate in parallel. So one could be taking liquor into the cell, one could be scanning, one could be flushing, one could be settling. They all operate independently. But within each FSS, within each of the sample stations, they go through the cell one at a time. Now, the frequency that you can actually want for the measurement, you can actually do that on the trigger from the DCS. So, for example, if you're looking at a digester, you may want to measure white liquor more often, and you may want to measure, let's say, the lower circulation more often. Then you can actually tell the analyzer to run through the trigger sent white liquor, the lower circulation, upper circulation, go back to white liquor again, go back to lower circulation again. So you can increase that frequency whichever way you want in terms of the actual trigger from the DCS.
All right, so I think there's the last 2 questions here that I'm filtering. So what are the maintenance requirement for this analyzer? Then that's the question. What is the maintenance requirements? What do we have to do yearly?
Okay, so that's a very good question. I alluded to earlier in terms of the actual maintenance requirement being lower. Now, I'll be honest here. If anybody comes and tells you that an analyzer requires no maintenance, you might as well just walk away from that meeting right away, because there's no such thing as a analyzer that requires no maintenance. What we're offering is a low maintenance system. So what the system needs is an annual maintenance, and the annual maintenance involved is you basically rebuild those valves that I mentioned, that I showed in the pictures. So we basically annually fix those valves to make sure they don't leak. We also replace the O-rings inside the flow cell. We change the light source. So basically, it's an annual maintenance item. We come into the mill and work with the system for about 3-4 days, and then the system is back online. So that's kind of the frequency of the maintenance requirement associated with this. Cost-wise, we can go through and detail those things, but the valve repairs, the repair cost associated with it's not much. The light source is not much, and so forth. So it's actually a very, very low system. Now, this is due to the fact that we can actually zero the system. We zero the system with that water reference every hour when we run the system. So even there's some changes associated with it, it can actually accommodate for those changes right away with the reference.
Okay, I think now with that last one, I don't think we have any more questions here. There's one that is if we can send the presentation, and after that we will send the link for you to watch the whole video, so you have the presentations and the video. Yeah, more than one person actually asked that, so yes, so we'll send you a link so you can watch it later as well. And I guess that's it then. So
great.
Thanks everybody.
Well, thank you very much
joining
again.
today.
Appreciate it, Enrique. Wonderful experience, and hope that we share some of our knowledge with the pulping community. And thank you for your time.
Thanks a lot for your time. Bye bye. Thanks for joining. Have a nice day.